Hey everyone, so today we're going to try to identify the test statistic and probability distribution for our hypothesis test of S&P 500 returns. So again, what are we trying to do? We're trying to look at the mean return or the difference between two groups, right? And so the question is the observed difference between these two means, is it due to chance or something entirely different underlying these values? So let's take a look at this t-distribution. So what we're doing here is we are assuming, first of all, that the populations are at least approximately normally distributed and that the samples are also independent of each other. So again, remember what we were doing. We're looking at the mean average returns, monthly returns before 2008, the end of 2008, and the mean average monthly returns after 2008. So these are our two sample means. And so what we're doing is we're assuming these two sample means are normally distributed and independent of each other, meaning that the returns after this event, 2008, and the returns before 2008 are independent, are not dependent on one another. So given that case, we can use this test statistic. I know this looks very complicated, but it's actually very simple. And all we're doing is, this is the t-statistic that we're looking for. And let's first take a look at the numerator here. What is the numerator here? The numerator here is just the sample means. So we're looking at the sample mean x1, x bar 1, before the event, and the sample means of the monthly returns after the event. And so we're looking at the difference between that. And then we're seeing, is that difference from our hypothesis or null hypothesis of 0? And we're going to say this whole term here is just going to be 0. And so the larger this numerator is, given this is constant, therefore the larger the t-statistic is. And therefore the larger the t-statistic is, the more confident we can be that the mean returns before and after 2008 are statistically significant, meaning they're different. And so now let's take a look at the denominator. What's the denominator? The denominator is the pooled estimate of these two samples. And so again, what are we doing here? We're assuming that we do not know what the population variances of these two populations are. We don't know the 60 months before and the 60 months after. We don't know what the population variance, but we are assuming that they're equal. And so if in that case, if we're assuming that they're equal, we can use this formula here to find the pooled estimate. And that is the pooled estimate of the two different samples. So now let's continue. Let's see if we can actually look at what a normal distribution looks like. So to do that, all we need to do here is let's import some libraries. So we're going to say from SciPy, import stats, and we're going to say import matplotlib.pyplot as plt. Run that. Hopefully that will go through. Pyplot, there we go. And now we can say x equals np.linspace. And we're going to say -3 to 3. And basically we're going to output 1,000 values into this x variable here. And so we're going to say plt.plot x stats.norm.pdf for probability density function, and we're going to put our x values in there. So we're going to plot that, and there's our normal distribution. So now let's see what our t-distribution looks like, which we're going to look at probability distribution for our t-distribution, given our degrees of freedom. And so remember, our degrees of freedom is just the minimum number of ways the system can vary. And again, we have our observed values. We can just take the observed values before the event. It will be equal to 60 months. And the observed values after the event, that's the 60 observed values after the event. And their degrees of freedom, all that is just equal to n1 plus n2 minus 2. We're going to output that. And there's our degrees of freedom, 118. And now we can actually output our t-distribution. So to do that, we're going to say xs is equal to np.linspace, -3 to 3, 1,000 value. And we're going to say plt.plot, and we're going to say xs stats.t for t-distribution.pdf, probability density function, xs df, degrees of freedom. We're going to output that, and there we go. And as you notice, it's the t-distribution is very close to the norm distribution. It's because we have such a large degrees of freedom, 118. Let's just say this was 2. So our degrees of freedom will be 2. What would that look like? There you can kind of see the difference between we have fatter tails, and you can see how different it is from the normal distribution. But since we have such a large number of samples that we're looking at, the closer it is to the population, we have a closer distribution that looks like the normal distribution. So that is us specifying the test statistic and probability distribution. In our next video, we're going to identify the decision rule, and therefore that decision rule will be used to see if our t statistic is larger or greater or less than that decision rule. So till next time, thank you.